Imagine a structurally flawless F-35 Lightning Tofan sitting on a runway.
Right.
Its aerodynamics are perfect. Its low observable coating is entirely unblemished. Its internal weapon bays are fully loaded with precision-guided munitions. I mean, it represents the absolute pinnacle of multi-domain military engineering.
The apex of physical combat power.
Exactly. But it cannot take off.
Yeah.
It remains completely locked to the tarmac because an unconceived vulnerability in a ground crew maintenance server has effectively paralyzed its onboard targeting computer.
The hardware's pristine, but the asset itself is neutralized.
Neutralized without a single kinetic shot being fired. Today, we are analyzing exactly why physical perfection is utterly useless in a multi-domain war if you do not comprehend the underlying systems that govern it.
It's a scenario that really highlights the diagnostic muddy waters of modern combat. The architecture of a strike package is no longer merely physical. It is an interdependent grid of systems functioning across domains that, well, they actively resist simple categorization.
Look, if you look at an aircraft and only see a machine, you are already operating at a massive deficit. Welcome to this deep dive. Consider this your briefing from the Blue Suit files.
Our parameters today are strictly defined.
They are. You are a technical sergeant candidate. Your career progression, and frankly, your operational utility to the force, rely entirely on mastering the systemic logic outlined in the 15 February 2025 Air Force Handbook 1, Airman. We are specifically cross-referencing Chapter 4, Air and Cyber Power, against the Airman Development and Testing Chart, or ADTC.
And evaluating the ADTC matrix for your required level of comprehension regarding Chapter 4, specifically Sections 4A, 4B, and 4C, the mandated standard is uniform across the board. You are required to operate at Level B.
We must define Level B with clinical precision right now before proceeding, because this distinction dictates everything that follows. According to the development chart, Level A is defined simply as remembering.
Which is basic retrieval.
Exactly. Level A is the basic retrieval of definitions, facts, and lists from memory. Memorizing the fact that an F-22 Raptor is a fighter jet is Level A.
And for a technical sergeant, Level A is completely insufficient.
It is. Level B is defined as understanding. This standard requires constructing meaning from written or graphic messages. It mandates interpreting, classifying, inferring, and explaining exactly how components relate to an overall structure.
Right. If you merely recite the aircraft inventory, you fail the requirement. Level B demands that you construct operational meaning from that raw data. You have to interpret why a specific asset exists, classify its function within the broader operational theater, and critically explain its systemic relationship to every other asset on the battlefield.
So to satisfy this Level B requirement, this briefing will systematically deconstruct the why behind the regulations, the physical physics, and the hardware inventory.
You're not going to walk through a table of contents.
No, we're going to build an operational matrix. We begin immediately with the analytic breakdown of Section 4A, identifying with Airpower. We must first establish the strict physical laws and axioms that dictate operations across the three distinct domains: air, space, and cyberspace.
And look, the terminology utilized to separate these domains is not arbitrary in the slightest. It is rooted in inescapable physical laws. The manual defines the air domain as the region above the Earth's surface, where aerodynamics generally govern the planning and conduct of military operations.
We need to isolate that term right there, aerodynamics.
Yes, aerodynamics involves the physical laws of airflow, atmospheric pressure, and atmospheric manipulation. An aircraft fundamentally relies on the friction and density of the atmosphere to generate lift over its wings and to feed oxygen into its turbine engines for combustion.
Which you have to contrast directly with the physical reality of the space domain.
Exactly. The space domain is defined as the region above the Earth's surface where astrodynamics govern planning and operations. Astrodynamics involves orbital mechanics and the physics of gravity and propulsion entirely outside of atmospheric friction.
Because you cannot maneuver a satellite using aerodynamic flaps.
Right, there's no air to push against.
And you cannot use an air-breathing jet engine.
Because there is no oxygen. You must classify these domains not by some arbitrary line of altitude drawn on a map, but by the fundamental physics that govern movement and survival within them. A platform designed for aerodynamics is catastrophically useless in a domain governed by astrodynamics.
Which brings us directly to the third domain, a domain which possesses entirely different architectural constraints, the cyberspace domain.
Cyberspace is defined as a global domain within the information environment. It consists of the interdependent network of information technology infrastructures.
So that encompasses the internet, telecommunications networks, computer systems, and embedded processors and controllers.
Yes, and it is vital to classify this correctly from a level B perspective. It is a fabricated domain.
Right. Unlike air and space, which exist in nature, cyberspace was engineered by humans.
Engineered by humans, yet reliant entirely on physical hardware servers, fiber optic cables, transmitters to project digital effects.
The manual breaks down cyberspace into three distinct operational components. To achieve level B comprehension, you must understand how these components structurally interact. Component 1 is the effectors.
Effectors encompass a broad range of signal-borne threats, both analog and digital. These are essentially the tools of execution.
Right. Component 2 is the medium. The medium is the access point that enables those effectors to reach their destination. So this includes the physical wired and wireless connections, the hardware, and the software pathways.
And component 3 is the targets. Targets include the weapons and systems themselves that utilize computers or networks.
The interaction of these three components forms the foundation of cyber operations. Joint Publication 312 defines these operations as the employment of cyberspace capabilities, where the primary purpose is to achieve objectives in or through cyberspace.
Understanding this basic architecture allows us to analyze the structural advantage of offensive cyber power. The text outlines 4 specific axioms here. They are misdirecting functionality, stealth access, exploiting vulnerabilities, and superior human cognition.
We have to analyze why these axioms inherently favor the attacker. The text presents a critical systemic flaw in the foundational architecture of this domain. From a warfighting perspective, the Internet has traditionally favored the offense over the defense.
And this inherent advantage exists entirely because of protocol design. The Internet protocols were originally designed for tolerance to failure rather than resilience to attack.
Wait, I want to clarify that mechanism. If a network is built to survive a massive kinetic strike by automatically rerouting data, which is what tolerance to failure generally means, why does that automatically make it easier for a cyber attacker to penetrate it? Those seem like two completely different types of resilience. Explain the structural flaw.
Well, it comes down to the mechanism of routing versus the mechanism of inspection. When a network is built for tolerance to failure, its primary directive is simply to ensure the message reaches its destination, regardless of which physical nodes are destroyed along the way.
It's just looking for an open door.
Exactly. The protocols are designed to blindly hand off data packets to the next available pathway. They were built to route information, not to inspect the intent, origin, or malice of that information. The system intrinsically trusts the data it is moving.
I see.
So the structural tolerance inherently favors the offense because the architecture itself facilitates the delivery of the weaponized payload. It does the attacker's job for them by actively finding a way to deliver the malicious code.
To counter this, the text suggests modifying the cyber domain for attack avoidance. It presents an analogy here. Just as a carrier battle group sails the oceans rather than remaining stationary to avoid targeting, a network or system can dynamically move around the IP address space.
Right. This creates continuous deception. It forces the attacker to constantly search for a moving target rather than focusing all their resources on penetrating a static defense.
The text also notes the implementation of anti-tamper protection technologies. These seek to reduce vulnerability by focusing protection only on the most critical components of a system, imposing exceptionally high penalties both in time and computing resources on the attacker.
But look, the ultimate axiom of offensive cyber power relies on the unknown. The text states this explicitly. Offensive cyber power is the exploitation of the unconceived vulnerability, where unknown cyber insecurity wins against known cybersecurity.
As a technical sergeant, you must infer the severe operational reality here. You are defending a system where the architecture itself works against you if the enemy locates a microscopic flaw you have not yet conceived.
You can patch every single known vulnerability, and you will still be fundamentally exposed to the unknown.
So transitioning from the physical and digital laws of the domains, we must apply these laws to the logic of global operations. For 76 years, the United States Air Force has operated as a comprehensive provider of military air power, projecting influence through 3 specific operational pillars: global vigilance, global reach, and global power.
We should pause here to acknowledge a specific instance of operational vagueness within the manual regarding these pillars.
Good point. When describing the mechanisms of global reach, the text states that Special Operations Forces conduct persistent engagements to enhance critical relationships and secure global access. We must clarify that phrasing immediately.
Right.
In a Level B operational context, Persistent engagements does not mean isolated one-off missions or temporary training deployments.
No, it means continuous, ongoing strategic relationships, embedded personnel, and maintained operational access in a region at a time and place of our choosing. It is the absolute architectural foundation of access.
With that clarification, we can categorize the three pillars. Global vigilance is the real-time, global intelligence and command and control network. It is the overarching ability to find, fix, and finish the smallest of targets across the globe.
Mechanically, that requires airmen operating multiple overlapping satellite constellations for uninterrupted situational awareness and nuclear warning, combined seamlessly with cyber operators defending the critical networks that actually process that data.
Then you have global reach, which is the mobility infrastructure. It is the logistical capability to range the globe rapidly, to respond to emerging crises, and to deliver critical combat supplies and personnel anywhere on the planet.
And this is not a theoretical concept. It is quantified by mobility airmen permanently positioned in 23 countries at 77 locations, operating a massive synchronized global system of airfields and supply chains.
Finally, global power. This is the kinetic capability. It is the ability to strike an enemy on short notice anywhere in the world, utilizing fighters, bombers, remotely piloted aircraft, and intercontinental ballistic missiles.
It encompasses special operators conducting daily counterterrorism missions and nuclear forces providing the ultimate continuous backstop for extended deterrence.
Understanding the overarching mandates of these three pillars leads directly into Section 4B, aircraft systems. Because to actually deploy global vigilance, reach, and power, the force utilizes a vast and highly specialized inventory of hardware. You must possess a clinical system of identification to classify these assets accurately and instantly.
The visual taxonomy of aircraft identification serves a distinct historical operational purpose. Historically, warriors carried brightly colored unit standards into battle for unit pride, rally points, and psychological impact. Today, that tradition is formalized in aircraft tail markings and roundels.
A roundel being a circular disc used as a national symbol on military aircraft.
Exactly. The manual notes the French Air Service actually originated the use of roundels during World War I. They utilized red, white, and blue concentric circles to represent their national flag and primarily to prevent friendly fire.
But the primary visual identifier on a modern airframe is the tail flash. A standard tail flash designates three critical pieces of operational information: the specific base the aircraft is assigned to, the unit or organization it belongs to, and the specific serial or tail number of the aircraft itself.
And it is critical to classify how this taxonomy has evolved for Level B comprehension. While units traditionally selected a single aircraft as a flagship with a highly visible, colorful fin flash for the unit commander and for public displays, standard operational tail flashes today are heavily regulated.
Right. They're predominantly executed in various low-contrast shades of gray.
The operational logic there is simple. Maintaining camouflage and reducing visual signature in contested airspace supersedes historical pageantry. You don't want to be a bright target.
Beyond external visual markers, the Department of Defense utilizes a strict alphanumeric symbol system for diagnostic identification. You must understand the logic of the Mission Design Series, or MDS.
The MDS designator systematically categorizes aerospace vehicles. This includes aircraft, guided missiles, rockets, probes, boosters, and satellites. The system is fundamentally split into two primary components separated by a dash.
The first component is comprised entirely of alpha characters. This letter describes the fundamental mission of the vehicle.
Right. For example, A stands for attack, B for bomber, C for transport, F for fighter, K for tanker, E for special electronic installation, T for trainer, and U for utility.
Stop right there and explain how to decode the rest of that string. How does a technical sergeant actually read the back half of that code?
So the second component of the MDS is comprised of alphanumeric characters describing the design number and the design series of the vehicle. A letter following the two-part designator indicates a specific model type or series, typically reflecting subsequent improved model designs.
So if you observe the designation F-15E, you construct meaning immediately without even needing to see the physical aircraft.
Exactly. F categorizes it as a fighter. 15 is the sequential design number, and E indicates it is a specific modified series of that original design. You are not just memorizing a proper noun, you are reading a highly specific system code that dictates its operational capability.
Which brings us directly to the core application of your Level B comprehension requirement, classifying the vast aircraft inventory outlined in Sections 4B and 4C. We will not mechanically walk through a table of contents or simply read a list of airframes.
No, that would be level A.
Exactly. To demonstrate level B classification, we will categorically analyze the operational logic of these assets. We will group them into simulated operational scenarios to demonstrate exactly how their physical designs dictate their capability to fulfill the doctrines of vigilance, reach, and power.
We initiate this analysis with Scenario 1, Global Power and the Penetrating Strike. To execute kinetic effects against a heavily defended adversary, we rely on strike and bomber platforms. We must analyze how varying aerodynamic designs achieve this singular goal differently.
Consider the A-10 Thunderbolt II. It is classified as a close air support platform. Its operational logic is built entirely around supporting ground troops in direct contact with enemy forces.
Therefore, it is structurally designed for excellent maneuverability at exceptionally low airspeeds and low altitudes. It requires straight wings to maximize lift at low velocity. This creates a highly accurate, survivable weapons delivery platform that can loiter over a battlefield for extended periods.
Contrast those low-altitude, low-speed mechanics directly with the B-1B Lancer. The B-1B is a multi-mission bomber designed for massive payload delivery. It carries the largest payload of both guided and unguided weapons in the inventory.
But its structural logic is entirely different from the A-10. It incorporates a blended wing and body configuration alongside variable geometry wings.
Meaning the wings can sweep back or forward.
Exactly. By sweeping the wings back, it achieves a highly streamlined aerodynamic profile for high-speed supersonic dashes. By sweeping them forward, it generates the lift required for heavyweight takeoffs and low-speed navigation. This combination of heavy payload and adaptive aerodynamics immensely enhances its survivability in contested airspace.
Moving to the requirement for stealth penetration, we examine the B-2 Spirit. The B-2 is a multi-role bomber capable of delivering both conventional and nuclear munitions. Its operational utility lies not in speed, but in its low observable stealth characteristics.
The flying wing design, completely devoid of vertical stabilizers and sharp angles, radically reduces its radar cross-section.
This structural logic allows it to penetrate an enemy's most sophisticated, overlapping air defenses and threaten heavily defended targets. Crucially, the text identifies the B-2 as providing the only all-weather hard and deeply buried conventional strike capability currently in the inventory.
The next iteration of this specific penetrating capability is the B-21 Raider. While currently in the development phases and not officially part of the active operational inventory, its systemic logic is strictly defined. It is designed to support the nuclear triad and penetrate modern, highly advanced air defenses with a long-range, mixed payload.
Wait, unpack the most critical structural feature of the B-21 mentioned in the text. Its open architecture design.
Open architecture means the software and hardware interfaces are not locked into proprietary static systems. It is built to seamlessly integrate new technology, new sensors, and new weapon systems as they are invented.
So it's an airframe designed specifically to adapt its internal systems and unconceived future threats without requiring a complete structural redesign.
Precisely. Finally, within the bomber category, we classify the B-52 Stratofortress. This is a long-range, heavy bomber performing strategic attack, close air support, air interdiction, and offensive counter-air missions.
The operational logic of the B-52 is sheer endurance and payload capacity. It has operated as the backbone of the manned strategic bomber force for more than 40 years.
It completely lacks stealth, but it compensates with overwhelming capacity. It is capable of dropping or launching the widest array of precision and unguided weapons in the entire inventory.
To complete the global power scenario, these bombers must be integrated with fighter platforms. Fighters operate at the critical intersection of kinetic strike and airspace control.
The F-15 Eagle is a perfect example. It's a dual-engine, all-weather, extremely maneuverable fighter explicitly designed to gain and maintain air superiority. It relies on advanced electronic systems and weaponry to detect, track, and destroy enemy aircraft in both friendly and heavily defended enemy-controlled airspace.
Its variant, the F-15E Strike Eagle, shifts that operational logic. It utilizes the exact same dual-engine all-weather aerodynamic frame, but it is structurally reconfigured for close air support, strategic attack, and deep interdiction.
Right. It possesses the capability to fight its way to a ground target over exceptionally long ranges, destroy the target, and fight its way out against airborne threats. To manage this massively increased cognitive load, it utilizes a two-person crew, a pilot and a weapons systems officer.
The F-16 Fighting Falcon provides a vastly different utility. It was a single-engine, multi-role tactical fighter with full air-to-air and air-to-ground capabilities.
Its systemic value does not lie in unmatched payload or twin-engine redundancy like the F-15. Its value lies in providing a highly maneuverable, relatively low-cost, high-performance weapon system that can be deployed in massive numbers.
We then step into the low-observable generation of fighters. The F-22 Raptor is a highly maneuverable airframe, heavily reliant on advanced integrated avionics.
And its defining feature.
Up there. Explain the physical mechanism of supercruise, which the text highlights as a defining feature of the F-22. Why is that structurally critical for stealth?
Supercruise is the aerodynamic performance capability to achieve and maintain supersonic speeds without using afterburners. Traditional fighters must dump raw fuel directly into their exhaust stream and ignite it to break the sound barrier.
Right, creating a massive thermal bloom.
Exactly. This afterburner effect creates a highly visible thermal bloom that instantly alerts enemy infrared sensors. And it consumes fuel at a catastrophic rate, severely limiting operational range.
So by achieving supersonic speeds on standard thrust alone, the F-22 maintains its low thermal signature, preserves its stealth profile, and massively extends its lethal range. It fundamentally alters the physics of the engagement.
It does. Then we have the F-35 Lightning II, which is categorized as an agile, versatile, high-performance fighter, but its operational logic relies on a completely different triad of capabilities. It utilizes stealth, but heavily prioritizes sensor fusion and unprecedented situational awareness.
It effectively acts as an airborne data hub, processing vast amounts of battle space information and distributing it to other platforms. It is designed to dominate the skies through data superiority just as much as pure kinetic performance.
But look, a penetrating bomber or an F-35 can neutralize a target, yet kinetic strikes cannot secure terrain, nor can they resupply forward operators.
That kinetic gap necessitates our next scenario. Scenario 2. Global reach and the logistics bridge. We must analyze strategic mobility assets. To understand global reach, let's simulate a massive deployment to an austere, contested environment. First, you must bridge the ocean with overwhelming tonnage.
That mandate belongs to the C-5M Super-Galaxy. It is one of the largest aircraft in the world, built for strategic intertheater delivery of outsized and oversized cargo and personnel.
Its defining structural advantage is its loading logic. The C-5M is designed so that ground crews can open both the front nose cone and the rear cargo doors,
allowing them to load and offload simultaneously.
Right. This drive-through capability drastically reduces cargo transfer times on the tarmac, minimizing the time the aircraft is vulnerable on the ground while maximizing throughput.
Once that heavy tonnage arrives at a main operating base, the C-17 Globemaster III provides a more flexible mobility function. It focuses on the rapid strategic delivery of troops and cargo directly to main operating bases, or critically, to forward deployment bases.
So it bridges the gap between massive intertheater transport and tactical delivery. It performs tactical airlift, high-altitude airdrop missions, and air medical evacuations, transporting litters and ambulatory patients.
But what if the destination lacks a paved runway entirely?
Then you need the C-130 Hercules. It is categorized primarily for the tactical portion of airlift missions. Its operational logic dictates functionality in highly austere environments.
Right. It is structurally reinforced and utilizes turboprop engines, making it capable of operating from rough, unpaved dirt strips. Because of this rugged baseline architecture, the basic and specialized versions perform an incredibly diverse array of roles.
We're talking tactical airlift support, extreme cold weather Antarctic resupply, aeromedical missions, weather reconnaissance, aerial spray, firefighting, and natural disaster relief. The C-130 airframe is heavily modified for distinct combat missions, resulting in lethal variants like the AC-130 gunship, the electronic warfare EC-130H compass call, and the special operations MC-130J command of the second.
The mobility category also includes VIP and special transport assets, which are absolutely critical for maintaining command continuity and diplomatic access. The C-20 Gulfstream III is a twin-engine cargo and passenger aircraft utilized for high-ranking officials, heavily equipped with worldwide secure and non-secure passenger communication capabilities.
The C-21 Learjet is utilized for rapid short-range transport into short airfields and can be quickly configured for emergency aeromedical evacuation.
The C-37 Gulfstream V fills worldwide special airlift missions for high-level government officials, again, heavily equipped with secure and non-secure voice and data capability to maintain command authority in flight.
The C-40BC serves explicitly as an office in the sky for combatant commanders and senior government officials, directly mirroring ground-based command centers. Finally, the VC-25. This fleet consists of two highly modified, specially configured Boeing 747-200Bs.
Its sole operational logic is secure presidential transport. When the U.S. president is aboard, the radio call sign is designated Air Force One.
But observe the systemic limitation here. Global reach and global power cannot be sustained. An aircraft cannot bridge oceans without the next critical category: refueling assets.
The tanker is the operational enabler. The KC-10 extender provides global in-flight refueling alongside airlift support. Its operational logic structurally combines the tasks of a tanker and a cargo aircraft.
It can refuel a squadron of fighters while simultaneously carrying the maintenance, support personnel, and ground equipment required for those specific fighters on overseas deployments. It also features the capacity to transport litter and ambulatory patients.
The KC-46 Pegasus is the newest addition to this critical fleet. We have to analyze its structural leap in capability. Older tankers often required ground crews to physically configure the aircraft for either a boom system, a rigid pipe used for Air Force assets, or a drogue system.
The flexible hose and basket used by Navy, Marine, and Allied aircraft.
Right. The KC-46 is engineered to conduct both boom and drogue refueling on a single mission. This fundamentally increases its flexibility in a joint force environment while simultaneously providing cargo and passenger airlift capability. The text notes the Air Force has begun taking delivery of the first of 179 KC-46As, adding to a total tanker fleet of over 400 aircraft.
Yet the manual explicitly documents a persistent need to field hundreds more to meet overarching national security requirements.
The legacy system supporting this entire structure is the KC-135 Stratotanker. It provides the absolute core aerial refueling capability for the force and has executed this mission for over 50 years.
Structurally, it features a unique design. A cargo deck sits securely above the massive internal refueling system, allowing it to hold a mixed load of passengers and cargo without interfering with fuel delivery.
And much like the C-130, the reliable 135 airframe serves as a stable base platform for multiple highly specialized modifications. This includes the RC-135 VW rivet joint for signals intelligence and the WC-135 Constant Phoenix for atmospheric collection.
And that intelligence collection mandates our transition directly into Scenario 3, Global Vigilance and the data network. These assets are the physical manifestations of situational awareness, because you cannot strike what you cannot see.
The E-3 Sentry operates the Airborne Warning and Control System, or AWACS. It is a highly deployable battle management platform. Its structural logic relies on elevating its massive radar dome thousands of feet into the air.
This bypasses the curvature of the Earth that severely limits ground-based radar.
Exactly. It provides all altitude surveillance, early warning, and tactical control for worldwide air combat operations. It directs, coordinates, and strictly controls joint air operations across the battle space.
The E-4B NAOC operates on a totally different logic. As the National Airborne Operations Center, it is not searching for enemy aircraft. It is designed as a highly survivable flying node of the National Military Command System.
It is hardened against electromagnetic pulses and provides critical, uninterrupted command and control in case of catastrophic national emergency, coordinating actions by civil authorities and military forces during severe crisis response.
The E-8C Joint STARS is a joint Army and Air Force program. While the E-3 looks up at aircraft, the logic of the E-8C focuses strictly down at ground targets. It utilizes advanced radar to provide near real-time, wide-area surveillance and targeting information on both moving and stationary ground elements.
This drastically enhances battlefield management for ground commanders.
The force also relies on highly specialized regional assets like the E-9A. This twin turboprop aircraft has a very specific operational parameter. It ensures the vast waters of the Gulf of Mexico are clear of civilian boaters and commercial aircraft during highly dangerous live missile launches and other hazardous military test activities.
Directly supporting weapons system evaluation and safety. For strategic, high-altitude intelligence, surveillance, and reconnaissance, or ISR, the U-2S Dragon Lady provides continuous, all-weather surveillance.
It delivers critical imagery and signals intelligence across all phases of conflict, but its operational envelope forces it to fly at extreme altitudes exceeding 70,000 feet.
This aerodynamic reality requires its pilots to wear full pressure suits, similar to astronauts, to survive the lack of atmospheric pressure. Operating closer to the ground, the U-28A Draco is part of the Special Operations Command Manned ISR fleet. It provides fixed-wing tactical support, surveillance, and communications relay specifically tailored to humanitarian, search and rescue, and highly sensitive special operations missions.
But the ISR mission is increasingly fulfilled by unmanned and remotely piloted platforms, permanently removing the human physiological limitations of endurance and risk. We must clearly classify the difference between these specific assets.
The MQ-9 Reaper is an armed, multi-mission, medium-altitude, long-endurance aircraft. It is a hunter-killer. It employs AGM-114 Hellfire missiles and GBU-12 laser-guided bombs.
Operationally, it is highly modular. Its structural logic allows it to be rapidly disassembled, loaded into a single standard shipping container, transported anywhere globally, and reassembled for rapid deployment.
The RQ-4 Global Hawk, conversely, is an unarmed platform. It operates at high altitude with massive long-endurance capability. Its mission does not involve kinetic strikes.
It relies entirely on a highly advanced integrated sensor suite to provide a broad, continuous spectrum of all-weather ISR collection to support joint forces globally, loitering over targets for hours or days at a time.
Our final operational grouping involves rotary, specialty, and munition systems. The CB-22 Osprey utilizes complex tilt-rotor technology.
By rotating its engine nacelles, it combines the vertical takeoff, hover, and precise landing qualities of a helicopter with the extended range, fuel efficiency, and high speed of a turboprop aircraft.
Its specific operational mission is the long-range infiltration, exfiltration, and immediate resupply of special operations forces in environments completely lacking runways.
The HH-60G Payhawk helicopter is dedicated entirely to personnel recovery operations. It is structurally and electronically designed to insert into highly hostile environments to recover isolated personnel. It is heavily equipped with specialized communication, navigation, and defensive systems to provide day, night, and marginal weather combat capabilities.
And the text notes the HH-60W is the advanced variant currently set to replace this aging, highly stressed fleet.
The MH-139A is similarly replacing an older platform, the Vietnam-era UH-1N Huey fleet. The Huey currently provides critical emergency response, security, and surveillance for off-base nuclear weapons convoys, as well as distinguished visitor airlift.
The MH-139A directly addresses dangerous capability shortfalls in the older fleet's maximum speed, operational range, loiter endurance, and payload carrying capacity.
The C-146 Wolfhound provides Special Operations Command with highly responsive, flexible operational movement of small, specialized teams needed to support theater Special Operations Commands across dispersed areas.
Finally, we classify the trainer fleet, which is the foundational system utilized for developing human cognition and pilot skill. The T-6A Tech Synthisin is the single-engine primary trainer where all pilots begin.
The T-1A Jayhawk is a twin-engine jet trainer specifically designed for students selected to fly heavy airlift or tanker aircraft, simulating those multi-engine dynamics.
And the T-38 Talon is the high-altitude supersonic jet trainer utilized for future fighter pilots, though the manual explicitly states the all-new technologically advanced T-7 Red Hawk has been selected to completely replace it.
To conclude our hardware classification, we must examine a vital component of Section 4C, missile and munition systems. Specifically, the manual highlights a unique asset, the ADM-160 Miniature Air Launch Decoy, or MEL-D. The MEL-D is a programmable low-cost flight vehicle. It is tiny. It weighs less than 300 pounds.
Yet it possesses an operational range of approximately 500 nautical miles.
Its operational logic is purely deceptive. It doesn't drop explosives. Provide an analogy to explain exactly how the system protects aircraft.
MEL-D basically operates like a digital ventriloquist. It doesn't just look vaguely like a plane on an enemy radar screen. It electronically mimics the specific radar cross-section, the flight dynamics, and the electronic breathing of a specific United States or Allied aircraft.
So an automated enemy surface-to-air missile site detects what it believes is a massive B-52 bomber approaching.
Right. It locks on and fires its highly expensive munitions at a 300-pound Ghost, entirely depleting the enemy's defensive arsenal while the actual bomber slips through completely undetected.
You have now reviewed the physical physics, the digital architecture, the visual identification systems, and the exhaustive hardware inventory. But remember the standard. Level A memorization of these lists and specifications is entirely insufficient.
We must now connect the dots. We must synthesize this raw data.
How do the hardware systems classified in Sections 4B and 4C actually execute the theoretical doctrines outlined in Section 4A? We must map the physical equipment to the doctrinal theory.
Consider the mandate of global reach. A strategic objective cannot be achieved if a combat asset cannot actually arrive at the theater of operations. We map the massive drive-through cargo capacity of the C5M supergalaxy directly to this pillar.
It brings the maintenance crews, the ground servers, and the munitions.
But a fully loaded C5M or a squadron of supercruising F-22 fighters cannot range the globe indefinitely without the KC-135 Stratotanker. The tanker fleet is the absolute foundational enabler of global reach.
Without the K in the MDS system, the F&B aircraft are geographically contained to their home bases. This proves the interdependent system logic. One asset's capability is utterly contingent upon another's.
We map the doctrine of global vigilance directly to assets like the E-3 Sentry AWACS and the long-endurance RQ-4 Global Hawk. They collect and process the massive amounts of data necessary to find, fix, and finish targets across the curvature of the Earth.
But vigilance is equally reliant on the cyber effectors described in Section 4A. Early warning networks, satellite communication uplinks, and digital over-the-horizon forensic analysis are required to detect anomalous signal-borne activity before it impacts the physical fleet.
Right, the radar dome on an E-3 is useless if the servers processing its data are compromised.
Global power is the kinetic result of this entire system functioning in unison. We map the stealth capabilities of the B-2 Spirit and the sensor fusion of the F-35 Lightning II directly to this doctrine.
But observe how interconnected the systems truly are in execution. A B-52 bomber relies on the 300-pound ADM-160 MAL-D decoy to act as a digital ventriloquist, saturating the enemy radar and duplicating flight signatures to ensure the massive bomber actually survives to reach its target.
The munition enables the aircraft executes the power. We must push this synthesis further to connect the cyber-physical divide. We cannot view domains in isolation. The four axioms of offensive cyber power, misdirecting functionality, stealth access, exploiting vulnerabilities, and superior human cognition are not limited to desk-bound theoretical network attacks.
An advanced aerodynamic asset like the F-35 is inherently reliant on its internal IT infrastructure, its sensor fusion algorithms, and its digital situational awareness displays.
Therefore, a digital cyber effector that successfully misdirects the functionality of an F-35's onboard targeting computer is just as lethal a threat to the doctrine of global power as an enemy surface-to-air missile.
The text explicitly states that unknown cyber insecurity wins against known cybersecurity. If an adversary successfully exploits an unconceived vulnerability in the ground-based maintenance network of a C-17 Globemaster fleet, global reach is immediately and completely paralyzed without a single physical shot being fired across the ocean.
The physical and digital domains are fundamentally and inextricably intertwined. You cannot defend one without mastering the other. We must distill this extensive briefing into the core deliverables required for you, the technical sergeant candidate. You have three primary takeaways based strictly on the Level B comprehension standard dictated by the ADTC.
First, you must be able to analytically explain how the differing physical laws of air, space, and cyberspace dictate all military operations. You must understand that aerodynamics requiring friction, astrodynamics requiring orbital mechanics, and digital protocol infrastructures designed for tolerance all require entirely different, highly specialized operational planning.
Second, you must understand the strict logic of the mission design series. You must be able to instantly read a seemingly random alphanumeric code and critically classify an asset's fundamental designed role within the joint force.
Third, you must be able to articulate exactly how the vast, diverse inventory of specific hardware functions, not as isolated tools, but as a single, highly interdependent system.
You must comprehensively understand how a 300-pound MAL-D decoy, a digital cyber effector, a ground-based server, a refueling tanker, and a massive C5M supergalaxy implicitly rely on each other to guarantee the overarching doctrines of global vigilance, global reach, and global power.
We must now outline the severe consequences of failing to achieve this required comprehension. If a leader merely memorizes facts, achieving only Level A proficiency, but fails to construct meaning at Level B, they cease to be an asset.
They become an active operational liability. A technical sergeant who knows that an F-22 goes fast but cannot conceptually explain the physics of supercruise or how a KC-135 mathematically enables its deployment range does not understand the system they are tasked with maintaining.
If you cannot critically explain why the Internet's original protocol design for routing tolerance inherently favors a malicious cyber attacker, you cannot adequately anticipate or defend the digital infrastructure that your physical aerodynamic assets rely upon to function.
You cannot lead airmen in a complex multi-domain conflict if you view the domains in isolation. I mean, ignorance of the system results directly in the collapse of the system.
We leave you with a final, chilling extrapolation drawn directly from the text's axioms on cyberpower. The manual openly and clinically states that in cyberspace, unknown cyber insecurity wins against known cybersecurity.
The fundamental architecture of the Internet inherently disadvantages the defense by prioritizing routing over inspection.
Therefore, we must ask the critical question. If the defense is inherently disadvantaged by the very environment it operates within, is the ultimate protection of our most advanced physical aircraft purely dependent on our ability to aggressively exploit the enemy's unconceived digital vulnerabilities before they discover ours?
End of briefing.